Hey there, everybody, my physics friends. Good to see you again, or whatever we're doing here. This is Sean Lally, and I'd like to talk to you today about torque and rotational equilibrium, or static equilibrium in general. So what we need to do first is review just a bit. There's a whole lot of information to talk about here, so this is probably going to be divided into two separate 15-minute videos. But let's just see how this goes first. So please stop the video whenever you need to write things down or to take it all in, or, as always, drop me an email for a quickest response to Sean P. Lally, P as in physics, at gmail.com. Okay, so remember there is a difference between scalars and vectors. Scalar quantities depend, that is to say, they are fully describable with only magnitude, things like mass, time, energy, and speed. Vector quantities, for a true description, require both mentioning of magnitude and direction. And this includes force, velocity, acceleration, different types of fields, momentum, which we just learned about, and torque, which is our topic du jour. So, generally in textbooks you see vector quantities being bold-faced or sometimes with an arrow over them. Now, why do we care? Well, we care because the mathematics of vectors is handled a little bit differently than that of scalars, especially because vectors being directional sometimes require us to break them into components. That can be left and right, up and down, plus and minus components. But when we talk about things like torque, it's a little bit stranger. I mean, sometimes we actually have to introduce a clockwise torque or a counterclockwise torque. So more about that to come shortly. So force is, of course, a vector. Force, which includes things like tension, compression, bending, other sorts of things. It's vectorial, and that is to say the direction matters. So we use the rules of vector math. You probably remember this, but it can't hurt to review it just a bit. So if we're adding displacement vectors, let's say we've got a hiker traveling 3 kilometers east and then 4 kilometers north. We can do a head-to-tail or tip-to-tail diagram, and we can see that their net displacement is 5 kilometers. And they, of course, could have reached the same distance by traveling 5 kilometers at an angle of arctangent of 4/3 north of east, if that, in fact, were possible. So, again, what we did was add vectors in a head-to-tail or tip-to-tail fashion. And the dotted line is the resultant vector. Now, so let's get into a little bit of greater detail here. So first of all, we're going to talk about static equilibrium. Static, of course, meaning stationary, not moving. Equilibrium. Part 1 is translational equilibrium. This is some stuff you saw earlier in the term, so I want to review it just a bit. In static equilibrium, we generally have to think in terms of two different types of equilibrium. There's translational, that is where the sum of the forces is 0, where all the forces balance out. And there's rotational equilibrium, wherein the sum of the torques, or moments, are 0. So, first of all, you know that F equals ma, of course. And if you have an object remaining at rest, at least translational, the sum of the forces has to be 0, which would mean that the sum, sigma, I should have put in there, of forces is equal to 0. Or another way to think of this is in terms of free body diagrams. Let's say, for example, we've got a person sitting in a chair. The forces acting on this person, well, we've got gravity acting down, of course, a normal or reaction force acting up. And if it's in static equilibrium, those two things have to be equal, of course. There could be frictional forces left and right. This is, however, not the only condition for static equilibrium. Let's take a look at a sample problem, then we'll get to the second condition in a bit. 40 pound, why in the world did I use pounds? Oh well, 40 pound stoplight hanging from a cable. And let's assume that it has some tensile strength. So what is the minimum diameter of the cable that you can use? I think actually I'm not going to bother with that part. I just want to determine what is the actual force in the cable. We'll save the tensile strength business and stress and strain for some other discussion. So let's say, again, if there's one cable, there's going to be 40 pounds of tension in it. If, on the other hand, there are two cables, well, if they are parallel with each other, it's not too surprising to learn that there's 20 pounds in each cable, of course. But if they are at some non-zero angle, that's a little bit tricky. We have to break it into components the way we did earlier. I am going to measure the angles with respect to vertical here, and In doing so, each cable, since they are of identical length, each cable is going to have the same tension T. So breaking them into components, and again, I'm measuring the angle with respect to vertical. So the up component for each of them is T cos 40, and the left component is T sine 40, and the right component is T sine 40. So, and of course, acting downward at the point of connection where the two cables meet the stoplight, that is 40 pounds of the weight of the stoplight. So how do we figure out the tension? Well, it's not too hard. We set the ups equal to the downs and the lefts equal to the rights. Okay, ups equal to downs. T cos 40 plus T cos 40 is 40. You could solve that. 2T cos 40 equals 40 pounds. Of course, the lefts and the rights, T sine 40 equals T sine 40. Geez, that's nice, but it's not very helpful. So 2T cos 40 equals 40, and solving that, you get 26 pounds in each cable. And if you had increased the angle, you would see that the angle has a giant effect on the tension. The tension will, in fact, approach infinity as the angle between them approaches 180 degrees. But that's for some other discussion. And as I said, of course, T sine 40 equaling T sine 40, true and not so helpful. Now, if they're not of equal length, it's the same problem. You just have to go back and set it up with a T1 maybe on the left and a T2 on the right. You'll have two equations and two unknowns, and then the left and right will be significant, as they were not in this particular example, but they will be important and non-trivial if the cables are of unequal length. And of course, there's other ways to do this. You could use a law of cosines, but honestly, I think that makes it a little more complicated than just solving it with components of vectors. Okay, now part 2, which is the main focus of the day. Static equilibrium. Part 2, rotational equilibrium. The sum of the torques or sum of the moments equal 0. So, first of all, we're going to define rotational equilibrium, and to do that, we have to define a new concept called torque. It is the product of force and lever arm. Don't confuse it with work, which is force multiplied by displacement. They have the same basic structure, and you might even think they have the same units, but they don't actually. This is where it gets tricky and very mathy. So, strictly speaking, we call torque a cross product, which is a vector product of force crossed into length. Now, don't worry about this too much, because I don't think you are dealing with dot and cross products yet in your math courses. But the net result is that it ends up being a vector. So most of the time we can avoid that complexity if we don't have three-dimensional vectors to deal with. And we really don't in this particular class. So don't worry too much about that, except when you calculate torque, it is going to be the component of force that is perpendicular to the lever arm. Okay, that's going to require us to use a sine function, as we will see in a moment. And by the way, another way to think about torque is just imagine holding something that's heavy. Now, if you hold it close to your body, it's not a big deal. But if you hold it like in an arm's length, boy, it will feel a whole lot heavier, even though, of course, it hasn't gotten any heavier. That is the beauty of the torque idea. It gives us a way to calculate this effect. So, okay. Let me make a brief distinction here between torque and moment. If you've had physics before, you might be used to the word torque, and indeed we're going to continue to use that word. But if you've ever studied any engineering, then you may have heard of the word moment, and it's calculated the same way. But I tend to use moment when I'm teaching engineering courses and torque when I'm teaching physics courses. I'm going to probably use moment right now, but please don't be too confused by it. It is still force times lever arm. And for an object to be in rotational equilibrium, the sum of the torques has to be equal, or the sum of the moments has to be equal. And that is, they have to cancel each other out. So, classic seesaw problem. Let's assume that we have a seesaw that's balanced to begin with. We're going to place a small weight and a large weight on opposite sides of the seesaw. Okay, how do they balance? Well, they don't have to be of equal weight, which is sort of counterintuitive if you think about it, but the reason they don't have to be of equal weight is because it's not all about the weights being equal when we talk about rotational equilibrium. It's about the torques or moments being equal. Moment is equal to force times lever arm distance on each side. So for these to be balanced, it has to be true that the moment or torque on the left has to be equal to the moment or torque on the right. That is, the weight 1 and weight 2 times their respective distances have to be equal. Weight 1 times x1 has to be equal to weight 2 times x2. That's the condition required for rotational equilibrium. And if you happen to have more than one weight, well, you just continue to add those on the appropriate sides. Yeah, in fact, you could have multiple weights on either side, and you take the sum of the moments or the torques on the left and the sum of the moments or the torques on the right, and they have to be equal to each other. Think about this for a moment. If you've ever balanced a broom on your fingertips, which end is heavier? Now, naturally, you probably think off the top of your head, oh man, both sides have to be heavier. If you cut it right there where the finger is, in this little drawing, it seems like they're both of equal weight. And of course, they're really not. So let's get to this in a second. We're talking about a weight distribution and not just discrete independent weights. So this is actually a little bit trickier. It can get into calculus, in fact, though we will, of course, avoid that for most of our needs. So we're going to define a new concept called the center of mass, sometimes known as the center of gravity, although there is a subtle difference between them. Center of mass of an object or system of objects is the point where all of these conditions are met. The weighted relative positions of the distributed mass sum to 0, which means that the torques and moments are balanced or equal on both sides, all sides. It's the point about which the object best balances and best rotates. It's the point where if you apply a force to it, the object will not rotate. It may move, but the object won't rotate. And it's the point where we can pretend all of the mass of the object itself is located. Imagine supporting a person. If you had to support a person with one hand, where would you hold that person? If you can imagine seeing gymnasts do this, they generally would hold it right around the belt line, a little bit above the belt line for a male, and a little bit below the belt line for a female. The center of mass is, in fact, not even always on the physical body itself, although, of course, for a person, it would be. So here's a couple of examples. Sledgehammer, the broom. The center of mass is very close to the heavier end. That's the point where the torques are balanced. But in the case of the center of mass of the sledgehammer, well, geez, oh whiz, the hammer part of the sledgehammer is way heavier than the handle. So they are not of equal weight if you cut it right at the center of mass. Same for the broom. They're not of equal weights. And if you look at something like a donut or a center of mass of a hula hoop, it's located at the center where there ain't no hula hoop. So again, thinking of the broom question, of course the short end is the heavier end. Here's a couple of other examples for you. Stable, an object's center of mass has to be supported with the balancing bird and balancing weights here. It's actually not right here. This is the strangest thing. You've probably seen a bird like this before. It's balanced on the fingertip right here because there are little weights at the end of each wing. Over here in this kinetic sculpture, there are weights. These are heavier weights on the left and the right side. But ultimately, it's balanced because the torques are balanced. And the forces, of course. Those white dots indicate the location, approximately, of the center of mass of the balanced thing. And again, it's important to note that the center of mass actually lies, in this case, below the base of support. It could be above, but in this case, it's actually below. The point is, however, it is supported. A couple of other things to take a look at. Gee, I sure wish we were meeting in person. I'd show you all this stuff face to face, but alas, we don't have that luxury. So, balanced nails, balancing dudes aplenty, another balancing bird, all kind of toys here. You might be able to tell that I'm obsessive about collecting physics junk. Oh yeah, here's one you can try here, a fork and a spoon balanced with a toothpick. I don't know if you can even make that out there, but, you know, a toothpick balancing a fork and a spoon on a bottle. And there's a, what else is in there? There's a Weeble and all kind of other junk. Oh, there's Ernest the balancing bear. He's great. He actually balances on a piece of string that you can stretch across the room. Balancing wine bottle. You may have seen that one before. If you take a look at what's even going on being balanced here, there's a meter stick that's being balanced. There's some weights on this side. The center of mass of the meter stick itself, the actual weight of the meter stick is acting through its center of mass, and it is balancing with the weight on the right side. More to come.